how much of our excess reagent is left over. So we're looking at finding out how much is left over for this one. So you've got to figure out how much was used. You know how much you have, right? You calculate that in the first part. So what you have to do is find the moles of limiting reagent, convert to moles of excess reagent, convert to mass, and then subtract mass from initial mass. Okay, and identify the intermolecular forces that were present. Which intermolecular forces are present in the first compound? Is it covalent or ionic? You should know this by now. Covalent or ionic? Covalent. So all covalent molecules have London dispersion forces. Are there polar bonds here? Yes. Is there going to be a net dipole? Yes. So it has dipole-dipole. Yep.
I have a question about the Lewis structure. Wouldn't it be bent?
Yes. It's bent. Which is why we have a net dipole. Yeah. But I drew it flat because I want to see if people know that. Okay? Yeah. So there's a net dipole here because this is not a straight molecule because oxygen does not form straight bonds. It makes bonds at an angle. Remember water? All the bond angles in oxygen are going to be the same. You're going to have an O, and it comes down to the C's. So you're going to end up with a net dipole. And it will be going up towards oxygen. So this has dipole-dipole. Can this hydrogen bond with itself? Why not? Because it can't. The hydrogens are attached to the carbon. What do you have to have in order to be able to hydrogen bond?
Hydrogen and oxygen.
Yeah, or?
Hydrogen with nitrogen.
Yeah. You either have to have an HO, an HF, or an HN bond. So there's no hydrogen bonding between molecules of this. CH3OH. What intermolecular forces are present here? Ask yourself, is this covalent or ionic? It's covalent, so it has to have London dispersion forces. Does it contain any polar bonds? Saad, what do you think? It does have a net dipole. Again, you've got an O, right? You've got an oxygen here. So you've got bonds that go like that. Difference here. is 1. Difference here is 1.4. You have a net dipole. So you have dipole-dipole. These are the kinds of questions you're going to see on your final exam. Can this hydrogen bond with itself? Jovan?
Yes.
Yes, it can. You can have hydrogen bonding between the H of an OH on a neighboring molecule and the lone pairs on that oxygen. Or that hydrogen is attracted to lone pairs of oxygen on a neighboring molecule. How about the next one? Is it ionic or covalent? Michael? Covalent. So what does it have?
London dispersion.
London dispersion.
Diplo and hydrogen bonding.
Yeah.
This is the OH.
Because of the OH. Now, this is going to have 2 sites for hydrogen bonding. This can make hydrogen bonds. This can receive hydrogen bonds. Because it has lone pairs of electrons on the oxygen. So a neighboring OH can the hydrogen can hydrogen bond to that lone pair of electrons on oxygen. So between molecules of the same substance, for this one, you've got 2 sites for hydrogen bonding. This one can make them and receive them. This one can only receive. Jovan?
So when you're drawing out the Lewis structure, you make it like bend, so you make it like this, it makes it a bend, right?
Yeah.
And when the O and the H on the right side are connected, you just make like a straight line between them? That's what you
Yeah.
bend.
It's up to you what you do there. So for those of you that are not as detailed orientated as Jovan is, if you draw it like this and you put in your lone pairs of electrons, it's fine. Jovan. Next year when we get to Vesper shapes, you're going to have to do it his way. Okay, so really, this one will look like that. But you won't have to draw it like that this year. Okay. So let's go back to the last one. Oh, that was bad. What happened here? I put CL4s on all of them. Why didn't you stop me? And it won't let me erase it. So here we go. CL. If I can't go back to that section if I've started a new section. It's weird. Okay, so here we go. 4 chlorines. Ionic or covalent? Abdul, do you agree? You don't really know? Does it have a metal? No, so it's not ionic. If you're never sure, check, is there a metal in the structure? If there's a metal in the structure, it's ionic. Only nonmetals, it's covalent. So this will have London dispersion forces. Does it have dipole-dipole? They cancel out if they have them. Don't forget that rule. In order to have dipole-dipole, you must be a polar molecule overall, which means you have a net dipole. You will not have a net dipole if you are a diatomic element or carbon bonded to an even number of only one element. So CO2, CCl4, C2H6. They will not have a net dipole. So this only has London dispersion forces. Are you okay with that part? Yep. But the number of the next element that it's bonded to has to be even. And only one other element. So it could be C3H10, propane. Nope. C3H8, propane. All right, Michael.
I have a question.
Okay.
Are all bonds with the diatomic element forward? Like, would that make sense?
All bonds within a diatomic element?
Yes, so like, for example, like the first three, right? They all have a diatomic element in it. So does that, would there be a polar bond if it has a diatomic element in it?
No,
Okay.
no,
Okay.
Are they all polar except for one?
yeah. Okay, so nice loud voice. Abdul, read for me what it says right underneath the table. Right? Nice loud voice.
The most soluble compounds will be those that can hydrogen bond with water.
Okay,
form
stop.
acid.
Thank you. Most soluble hydrogen bonding with water. So if you can't hydrogen bond with yourself, chances are, unless it's a specific atom in there, you're not going to be able to hydrogen bond with water. You're going to need an O, an N, or an F. Keep reading. Thank you.
The moderately soluble will be able to accept hydrogen bonds from water but not form them, and the insoluble will not be able to form any hydrogen bonds with water. Now group them as soluble, moderately, or non-soluble in water.
All right. So it's saying if you can't hydrogen bond, you're not going to be very soluble. If you can accept hydrogen bonds, but you can't make them, you're going to be moderately soluble, and you're going to be very soluble if you can make and receive hydrogen bonds. So, bottom one, it doesn't form any hydrogen bonds. It's not going to be soluble. It can't hydrogen bond with water. So the bottom one, not soluble. So, top one, it doesn't form hydrogen bonds. Can it receive hydrogen bonds? Yes, because it has lone pairs of electrons on oxygen. So there's a chance that it could accept hydrogen bonds, so it would be your moderate. Okay? So that leaves the middle two. Can they make hydrogen bonds? Yes. So they are going to hydrogen bond with water because it also contains OH bonds. Can one of them form more than the other? Is there more than one site on one of them?
Third one, CH3COOH.
Yes. This third one has two sites for hydrogen bonding, both on the C double bond O and the OH. So because it's got more sites to hydrogen bond with water, it is going to be more soluble in water. You also have to take into account how many carbons, though. If you've got 10 carbons, I don't know if you've talked, anybody here taking biology? Have you talked about hydrophilic and hydrophobic? You will. Have you talked about cells, cell walls, and membranes, and how they're two parts? You have an outside and an inside. What are they made up of? What are the cell membranes made out of? You talked about phospholipids? Lipids? Fats? Has he shown you something that looks like this? That's what your cell membranes are made out of. And gaps between them are how ions get in and out. So the head and the tails are different. One's hydrophilic, one's hydrophobic. Which one do you think doesn't like water? Hydro. The phobic, the hydrophobics will go together. This is why these come in, because the outsides have water, cytoplasm. So these heads are hydrophilic. They will be out towards where the water is. The insides are hydrophobic. They go together. And they create a membrane, a barrier. This is how soap and detergents work. Soap particles will have a hydrophobic and a hydrophilic part. And they basically form circles around the particles. So it's not like they're breaking it down when they're getting rid of all the grease and the dirt on your plates. They're surrounding it. The hydrophilic parts will be towards the water. The hydrophobic parts will be in together, and they actually scoop up particles in between them. And that's how soap works. Okay, so the longer the carbon chain, the less soluble, even if it has the same functional group. The same group of atoms on one end. Okay, this is a really important thing you need to remember. And because some of you don't listen when I speak, some of you will claim you've never ever heard this. When you dissolve a substance, water is not a reactant. It's a solvent. It does not chemically change your substance. You go from a solid or a liquid to an AQ. That's it. That's it. That's it. So if you have a covalent molecule, let's say you've got sucrose. My favorite substance in the whole wide world. I dissolve sugar in my tea. Sugar amount is actually smaller than the water amount in my cup. So my water is my solvent. That is how you show dissolving of a covalent molecule. How many people here make spaghetti or pasta? What do you usually put in the water before it starts boiling?
Salt.
Do you know why?
Make things not stick.
No, that's why you put oil in it.
Boil.
Makes it boil faster, hotter temperature. It's not just that it happens faster, it's because you're actually, when you have boiling water on your stove, if you have 2 pots, equal amounts, same size, same pots, you boil one, just pure water, you boil another one with salt. The one with salt is boiling higher than 100 degrees Celsius. It's faster because you need to put more energy in to bump out the salt molecules. Out of the way so you can vaporize it. So you can overcome these intermolecular forces. It's called colligative properties. You do it in university. But that's why your pasta cooks faster with salt water, because it's cooking at a higher temperature. Some people like to add it for taste. So if I put some salt in my pot, what happens to my salt? It dissolves. Solid to aqueous. That's it. That's all you're doing when you're showing dissolving of a substance. Okay, so you can represent dissolving this way, or actually in a beaker, you don't actually have particles of sodium chloride surrounded by water molecules. If you've got AQ, what you actually have in the water is ions. What's the charge on sodium? Just 1. What's the charge on chlorine? So that's what you actually have in your beaker. If I say write the chemical equation for the dissolving of a salt, you can write either way, but I'm telling you now, you're going to need to know this in this unit, because you're going to figure out how much of an ion is formed. So draw a beaker. Put some water in it. And I tell you that you have dissolved sodium fluoride. How would you represent that in your beaker? Yep. If I've got a beaker, you notice there's no waves in my beaker, because there's no wind on the surface. I will have, what did I say I was dissolving? Sodium fluoride. I've got sodium ions and fluoride ions. Now, let's say you've got, do the same thing if you've got lithium chloride. Draw a beaker. Show what you would have if you dissolve some lithium chloride. What would your beaker look like? Alex? Li plus and you would have Cl negative. Floating around in the liquid. Now, draw what you would have if you dissolve some magnesium chloride. What do you have in the beaker?
Would this be written as like 2+? Like you have 2 pluses, and then like magnesium 2+, and then chlorine 1. Oh no, it'd be the other way, right?
Chlorine stays 1-. That doesn't change. But you need another one. Because the formula for magnesium chloride is MgCl2. Are you okay with that? This is going to be really important when we're trying to figure out the concentration of magnesium and the concentration of chloride. Because you have twice as many chlorides in solution as you do magnesiums. So if I have a liter, and I have 0.1 mole of magnesium chloride dissolved in there, I will have 0.1 moles of magnesium and 0.2 moles of chloride. Because for every one that broke up, I formed twice as many chlorides. Are you okay with that? Does that make sense? Speak now. Yeah. Does this make sense? Yeah?
How come if you start out with 1 mole, you end up with
Then convert to chlorine. So we're going to use the mole ratio. Okay?
I got the moles for
You got the moles?
Yes.
So now you're going to convert to moles of chlorine. For every 2 of these, we need 1 of those. So you're going to take your moles of Na and multiply them by 1 chlorine over 2 sodiums. Do you know where I got the 1 and the 2 from? Okay. And then you convert moles of chlorine to mass. Using that formula. And then multiply answer by 1.10. So that basically is 110%. So your answer plus 10%.